construction of free field coordinates in the Schwarzian theory, or well, putting more mathematical words probably would be the coordinates for certain real zero coadjoint orbits. And this is work in progress with Anton Alexeyev and Olga Shekharis. And so yeah, let me introduce the main player of today's talk. And the main player will be the Schwarzian theory. And so the whole conference was somewhat hiddenly about the Schwarzian theory, parts in physics, parts in math. And I just want to say that there are these wonderful, nice relations with physics theories like the SYK model or JT gravity, and we heard a little bit about it the last week. But also, like in a more pure math sense, for example, with the asymptotics of Virasoro characters. And if I would kind of try to explain what the Schwarzian theory is, and I would talk to the physicist, I would probably say words like the following. So we want to kind of build a one-dimensional quantum field theory or like quantum mechanics. So I would say, okay, our fields of the theory, they're orientation preserving diffeomorphisms of the circle, where the circle I think as being just compact time. And so there's functions from R to R, which have a positive derivative, first derivative, and they satisfy this quasi-periodicity condition. And then I would say, okay, now I gave you a space of fields, I should give you an action functional, and then I would kind of have a model. So the action functional would be the integral over the circle, some df dash squared plus c times the Schwarzian of f, where b here is a constant. We take it to be a constant. More generally, it can be a quadratic differential, so it can be a function as well, quadratic function. And c is a constant, which is the central charge usually. So, and then we would be interested in calculating correlation functions, which would be given by 1 over the partition function, so a normalization of the integral over basically our fields, probably model some symmetries, some measure of exponential of, let's say, the scaled action. So this would be some kind of coupling constant or not. And then we could have certain insertions of certain operators. And here I just want to point out that this measure, this part integral measure, we think of it as, well, this infinite and probably very ill-defined thing, but it looks a bit unusual. Okay? So usually we're used to just saying, okay, we just integrate over just the fields, but it's the fields over f prime, which is somehow this invariant object, which we should integrate. Okay, and then our task would be basically to calculate these correlation functions. So if I would talk instead to a mathematician, I would probably say the following words. I would say that these space of fields, probably the symmetries, so the space we are integrating over, are actually the diffeomorphisms of the circle modulo the stabilizer of this b, where this small b, as I said, it's actually it's not just a constant, mathematically it's a quadratic differential, but we take the constant quadratic differential on the circle. It can be seen as an element of the dual of the Virasoro algebra. And then this plus S1 over the stabilizer basically says that this is a Virasoro coadjoint orbit. Through this element B. And then this action functional, so then there's this observation that in fact there's an S1 action on the orbit which just rotates kind of the loop. So it sends f of x to f of x plus theta, let's say. And it just turns out that this action functional, so S of f, which is this expression, is actually just the moment map for this S1 action. Where on the orbit we have the symplectic form, which is the Kirillov constant Zoryuk symplectic form, the KKS symplectic form, which I will write down a little bit later. And yes, and then these correlation functions up to normalization, what they are basically orbit integrals. So it's an orbit, an integral over the orbit, the exponential of some parameter t times the symplectic form. The moment map, and then we would have to put a certain measure, and this measure will be the one coming from the symplectic form, so the Liouville measure. And in particular, this would be nice, so depending on actually the operator insertions we put here, or like the functions on the orbits we put here, this can be computed by localization or not, right? So let me just say that we have this normalization here. So an example, if we just would like to calculate the partition function, or what we call the partition function, this would be just integral of the moment map, or exponential of the moment map, by the symplectic measure over the orbit. And now this kind of gives us already the realm that formally we could compute this by some localization techniques, namely the Dustomat-Heckman technique, simply because we're integrating, well, the moment map of an S1 action over our symplectic space. So this would be formally a formal Dustomat-Heckman integral, or localization integral. Okay, so what does this have to do with what I call free-field coordinates? Well, basically we kind of took this theory, which we can think in terms of these physics words or in these math words, but in the math words there's this whole business of symplectic geometry and Hamiltonian group actions on it. And in particular, if we have like a symplectic manifold, we would like probably, well, they are very nice coordinates. And these coordinates, these are so-called Dabou coordinates, and this is what I would call free-field coordinates. And these coordinates, they kind of give us a nice form of the moment map, which then becomes just quadratic, and the symplectic form, which is basically a constant symplectic form. So in finite dimensions, we have basically the following theorem, which we can call the Equivariant Theorem, which says that if we have an Hamiltonian, so I do it just for S1, I think one can extend it to a torus, but let me do it for S1. Action on a finite dimensional symplectic manifold, so this action is Hamiltonian, and it has moment map mu. Then there exist coordinates xi, yi around each fixed point of this action. Let me label the fixed point P, such that basically we have two things, namely the symplectic form just becomes the usual symplectic form, dxi with dyi, and mu becomes the moment map evaluated at the fixed point plus 1/2 sum over I ai xi squared plus y I squared. And let me just write this in kind of complex coordinates. So if I think of zi as being xi plus iyi, then we would have something like I over 2 pi here, and here just d zeta, sum over j, d zeta by j, and it will be u of p minus. This is this plus 1/2 j d j squared. So that's kind of the theorem. So then a natural question, so this is very nice, right? Because as I said, I kind of outline here and then we'll foreshadow again. This action here, right, is just the moment map. So if we would be able to find these kind of coordinates, then our action just becomes quadratic and it would be Gaussian. And we would be in a free theory, right? So this is kind of the thing we want to do, and the whole talk will be about finding these or constructing these coordinates for a special class of orbits. But there's one more thing I should say about this. Namely, there's this question like, how big is this W chart? Okay, so how big is this W chart? And the intuition or naively or intuitively, let's say, this chart can be extended until the next fixed point. So let's see an example what I mean by this. So if you take the S1 action on S2, which is embedded in R3, so we just have our sphere. Here we have the north pole, the south pole, and the S1 action just rotates along the z-axis, right? Then we can write the symplectic form on the sphere as being dz with d phi being the angle which goes basically around the z-axis, and that being just the height function in R3. Okay? So then the moment map. So S1 is generated by dd phi. And the moment map is just, in this case, the height function. So now, if we look at the like a small neighborhood here around n, so at z is equal to plus 1, then there exist coordinates 2 z minus 1 cosine phi 1 2 z minus 1 sine phi, such that omega becomes just dx dy, and mu becomes 1 plus 1/2 x squared plus y squared. Okay. So these are indeed our nice double coordinates. Now we can ask, okay, how big is this chart? Meaning, when are those coordinates ill-defined? And they're ill-defined at the south pole. And they're ill-defined at the south pole because the angle phi doesn't make sense. Kind of, this is ill-defined there. However, at the north pole, we don't have a problem because basically this vanishes. Okay. So we just get 0. It's centered around the north pole. So indeed, we can kind of go all the way until we can extend this chart all the way to the south pole, or like basically any finite distance to the south pole. These are good coordinates. So they're extendable. So good coordinates. 1 is 2 minus the south pole. Okay. So let me. Yeah, you can see from here, right? This is good. And now here, is a crucial observation. So not only these coordinates are very nice, right, and our theory would be just a Gaussian theory in these patches, but also there's a crucial observation saying that basically there exist many orbits, or a huge class of orbits, such that the S1 action, which I pointed out here, which basically just translates the diffeomorphism, which is the rotation of the circle, has just one fixed point. Namely the class of the identity. But if it just has one fixed point, and naively we can extend kind of this chart until the next fixed point, this would mean that we would create a global chart, a global double chart. So naively, we can think that there should exist a global double chart. And so what I kind of want to talk about in the rest of the talk is how to find this global chart for hyperbolic orbits. So I want to talk about the construction for hyperbolic orbits. So we've seen on Wednesday that there's a classification, complete classification of these reciprocal coadjoint orbits, and they fall into like hyperbolic, elliptic, and some other special orbits. And we will take a certain class of them. Okay? So if you, just a reminder, if you remember, the classification had this nice diagram which was flashed, where they had these little dots here, and we had something like a parabolic orbit here. We had like special and elliptic. And we're going to focus here. I just want to flash this diagram to remind you, and I will say a little bit more what this means for kind of the parameter b which we had in the game.
This was for the universal cover of SL2?
This is the classification of these Virasoro coadjoint orbits. And then, if time permits, and I think it will permit, I just want to talk a little bit about these correlation functions of certain observables, and the observables we kind of get some intuition from the physical side of the story, which are the bilocals, because that's what people are most interested in. So this is the plan, but now I should basically tell you one attempt to find these free field coordinates and its advantages and probably its drawbacks. Okay. So let me just recall a little bit of notation. We will parameterize our diffeomorphisms by again functions from R to R, which satisfies that they have positive derivative, and f of x. And let me call the length of the inner circle L, just to keep track of all possible lengths and all possible parameters which we can find in the game. So there, these functions, they're quasi-periodic. We take b to be a constant, and points in the coadjoint orbit through b, what we need to know is just that they're labeled by this tf of x, which is precisely what we've seen before, like b f dash squared plus so x plus c times the Schwarzian of f. So c is also constant. This is the central charge. And then, since we're working with coadjoint orbits, I just want to flash how the symplectic form looks like. So the symplectic form can be written as an integral over the circle of delta tf of x, basically, which delta f over f prime, or if we spell it out what this actually means, then this can be written as integral over s1 e delta f, which delta f, and there's a prime here, plus c over 2 delta of the logarithm of f prime which delta of the logarithm of f prime prime. Okay, so it's not a very easy formula, right? Somewhat. So this is much easier, but this is basically just saying it's the KKS symplectic form. But okay, we have an explicit expression in terms of these r. And then I just want to recall again that we had this S1 action, which sends f of x to f of x plus theta, and it was Hamiltonian. And the moment map is basically the integral of t of f of x, which of the circle, which will be our action if we think in terms of physical terms, right? This will be our action functional. Okay, so as a first step towards these free field coordinates or these taboo coordinates, we are going to do some transformation, some coordinate transformation, and see that due to the transformation properties of the Schwarzian, we can simplify. So consider a function g from R to R, which has positive derivative, such that the Schwarzian of g is equal to b over c. Okay? So then if we let f to be just a composition of g and f, then due to the transformation properties of the Schwarzian, we can write actually these points in the orbit just by a Schwarzian of the big F coordinate or big F field. And at the same time, omega becomes c over 2 integral of this 1 delta log f prime, which delta log f prime prime. And if we would do a further change of coordinates, which is suggested by the symplectic form, right? So we just call u log of f prime. Then actually we can show that omega becomes quadratic indeed, so delta u, which delta u prime, but also that mu, which was the integral of t of f, will now become the integral of u prime prime minus so c 1/2 u prime squared dx. And as long, and so now we of course have to think a little bit about properties of this big F and of this little u, like for example periodicity conditions. But it seems, or as we will see, this u prime prime is always kind of periodic, or it should be periodic. So this would be just a total derivative, and thus we would just have a quadratic action, right? So the moment map just becomes kind of the theory of a free particle. And we would, in principle, be able to do all the calculations quite explicitly, because everything would be just Gaussian integrals. And I think we can do Gaussian integrals or localizations. All other integrals are probably impossible to solve. So this is very good. Just one more remark, basically. If we now talk in physics terms and think about this path integral measure, right? How does it look in terms of this u? So let me just recall that this path integral measure was something like this. So now in the f variables it just stays the same. But in the u variables it just becomes flat. So indeed, if these coordinates would be good coordinates, we would just have a free particle theory. Okay, so why am I saying, okay, they would be and not they are? Because there's small subtleties we need to check. And I'm going to present kind of the good case first, right? Good news before bad news, and then the bad news afterwards. So the good news are as follows. So our task is to find, so I should of course tell you something a little bit more. namely that I was cheating a little bit, that this is not yet the full term, but there will be some kind of integration by parts, right? And if we think of this to be just the integral from 0 to L, which is our circle, then there is a boundary term which goes as follows. So we're not only supposed to find a function such that g prime is bigger than 0 and the Schwarzian is just given by this constant, but also we kind of want that this is supposed to be periodic. So we don't want this thing, meaning that g prime prime over g prime is supposed to be periodic. Okay, so our task to find g with the property that the Schwarzian is a constant and g prime prime over g prime is a periodic function. Yeah. And to find g, we have a look. So, for example, here's one attempt. We can have a look at Hill's equation, which already played a prominent role in kind of this classification of these Virasoro coadjoint orbits. And this Hill's equation, why actually they play such a huge role is because, so the equation looks like psi dash dash plus t of x psi is equal to 0, where psi is, where t of x is periodic. And if psi 1 and psi 2 are independent solutions, then there's a nice observation, namely that the g, the quotient of these solutions, satisfy that the Schwarzian of g is equal to 2t. But we want it to be b over c, which means we just look at a particular Hill's potential, and we just want to study the solutions of psi dash dash plus b over 2c psi equal to 0. But this, okay, now this we can do. Yeah. And there are two cases which we want to look at. So the first case is that b is smaller than 0. And these will be these hyperbolic coadjoint orbits. So whenever I say hyperbolic, I mean just that b is smaller than 0. So then let us introduce this parameter.
Sorry, and you assume c to be positive, right? Then
Yes, absolutely. Yeah, c is always positive. Yes, absolutely. Otherwise, we would have a flip. Yes, thank you. So if we would introduce now just the following combination, so since b is negative, this is a positive number, then our equation just looks like 1 over 4 alpha squared psi, and this is solved by psi 1 e to the alpha x2, psi 2 e to the minus alpha x over 2. And then we can check that g is now e to the alpha x, so psi 1 over psi 2. And let me introduce some normalization kind of constant here. And indeed, one can now check with this explicit kind of notion for g that the Schwarzian of g is indeed b over c using kind of the parameter alpha, and that g prime prime over g prime with something like alpha, which is a constant, is periodic. So this is very good. Let me just spell out then how the other variables in our Darboux construction look like. So for example, our f field now is just e alpha f of x over alpha, and it's not quite periodic, but it has this monodromy, or this multiplicative quasi-periodicity. And however, one can show that the Schwarzian of f now is periodic. And then the free field coordinates well, our double coordinates are just log f prime, so they look like alpha f plus log of f prime, and they satisfy that u of x plus l is u of x plus alpha l. Okay, and just one small remark. Going from f to u is 1-to-1. So one can find, so one direction we have, right? So u in terms of f, and the other term one can kind of integrate. So that's actually very nice. So in particular, for kind of more physicist-minded audience, I want to just say that u, right? So we know already that the action of u is just a free particle. But now we kind of have the free particle which is compactified on some kind of circle with some radius. So this is something we should be able to do. Okay, so since this construction kind of seemed to work actually for any u, right? Let me show that it's not quite true. So, do you want to say this? I want to do the remark first. So, well, to actually find the good double coordinate, this would be just the Fourier modes of this function, right? So this in particular means that u of x can be written as alpha x plus some periodic function, I over L in this case, n times x, and then u of, also here we identify u minus n is u bar of n. And then basically the UNs for n not equal to 0 are the good coordinates on our orbit. Okay. So we kind of covered the case b is smaller than 0 for the hyperbolic things, and everything seemed to work. So we actually found our double coordinates, which kind of was in the beginning very non-trivial because finding double coordinates is actually very hard, unless one has a clever guess. So let me show you what actually goes wrong, because now the naive question would be what for b bigger than 0, which would be the elliptic orbits, right? Which kind of, I think, got the most interest so far in the literature, at least in the physics side. So like these SYK models, the JT gravity, they kind of come to these elliptic orbits, especially to these special or exceptional orbits. So for example, in particular, b equal to 1 is very interesting because this is supposed to be like kind of the universal, universal Teichmüller space. So there's like a lot of research also in pure math, I think, going on for b equal to 1. So it would be very nice actually to find double coordinates here. But why does this method or this approach actually fail? Well, here it goes. So again, we can define this parameter alpha, which now is just b over 2c. And then this is just a harmonic oscillator, basically. So saying that our solutions are sines of x and cosine of x. So our function g then will be tangent of x, right? And kind of, so this f, so it still satisfies that the Schwarzian is g over b over c. It still satisfies that g prime prime over g prime is kind of periodic. But one has to be much more careful here, of course, because one kind of, I mean, this is a singular function, right? So especially for alpha, being like 2 pi an integer or something, we get to these exceptional orbits, and there's really a problem because like we go to infinities. But we will see that we will get a problem anyways. So let me just normalize here, and then f would be just the famous or infamous tan transformation, which people in the literature talk quite a bit about to simplify the action. So this is kind of this tan transformation, which is in particular known in the physics literature. Yes, very good. So now I just want to point out that our u variable was defined as f prime equal to the exponential of u. right? So U was the log of F prime. So now here arises the problem, which was absent before, namely, suppose we can actually find x plus and minus such that alpha f of x plus minus is, for example, plus minus pi over 2, let's say. Then we could look at this, yeah, well, I would say rather ill-defined quantity fx plus minus fx minus, which would be the integral from x minus to x plus f prime, which naively, well, would be the integral of our exponential of u. But this seems to blow up, right? So in physics, what one would do is kind of, okay, we would kind of forget about this, but so what it says is that we get a constraint on the u field, namely that the exponential of the field, if you integrate between these special points, it blows up. This is a constraint. But since we don't like infinities, we would kind of forget about this part, and we would say, oh, let's introduce a regulator, lambda, and we say that, okay, at some point we take lambda to infinity, for example. Nevertheless, we would have to deal with this constraint. So even though our action looks like a free particle, this particle is not free because it's subject to this constraint. And then how to deal with these constraints kind of in physics. So for example, we can kind of lift the constraint into the action functional using Lagrangian multiplier, let's say lambda. We would an action functional, which now would look like a free particle, plus lambda, yeah, basically this integral, right? Something like that. Okay, so well, we can basically shift actually this x minus and x plus to the endpoints of our interval because we have some more freedom, which is like an S1 freedom in terms of f. And then if we would do this, we would arrive at something which looks like Liouville theory. Okay, so we would, instead of a free particle, we would have like some kind of 1D Liouville theory, which is much harder to solve. Okay.
Sorry, can you repeat again? Why is that? What precisely is the problem in there in the first line or in the first?
Here.
No, I mean about on the top.
Here?
What was the problem there?
This is a constraint for the particle.
Right, but didn't you say that? I mean, you already put some constraint on f in the first line, right? You're saying that f.
No, this is small f. I just find these coordinates. This is just for x plus minus. So I find coordinates such that basically the argument of the big F kind of blows up. I just want to find the singularities. So the big F.
Okay.
F of x.
Yeah, it blows up in f.
Yes, exactly. Okay, but so this method at least, or very nicely actually, it gave us free field coordinates for the hyperbolic orbits. And so now I want to consider just the cases where b is smaller than 0, such as we're in the hyperbolic case, and kind of show how to calculate correlation functions, because now we can do actually everything explicit. So let me first talk about observables. I want to do a small detour, which is a bit hand-wavy, but it gives like a very nice idea of how to view these observables which come or which appear in the literature. Okay, and this goes a little bit as follows. So there's the slogan which is which can be made precise is that if we take, let's say, SL2R, or let's say the universal cover, the F theory on the two-dimensional disk, then there's an operation called Sympathetic Reduction. Then we get to the Schwarzian theory on the boundary of this theory. So let me just sketch the idea. So the idea is that this action, so now I will heavily use physics words, so the action of the BF theory looks something like a scalar field times the curvature of a connection, which takes values in the algebra of SL2R, plus, let's say, some boundary term to make, like the variation principle well defined, and one can include a certain Hamiltonian. But the important point is that B is a Lagrangian multiplier, so the theory kind of localizes to flat connections. But since we're on a disk, this means that every connection is kind of pure gauge. And it actually turns out that this group valued field is actually in omega g, or lift of this loop. It descends to a based loop. And now for this SL2R story, there exists this Iwasawa decomposition, which we've already seen also on Wednesday, namely that G can be written as, like any element in G can be written as a product, kind of in a rotation matrix, or the lift, if we think about the lift, diagonal matrix and an upper triangle or lower triangular matrix. So in particular, then one observes that this loop-based loop space is actually symplectic space, and one can act by basically right multiplication, let's say, with loops in N, right? And this turns out to be actually Hamiltonian. And now, since we have kind of a symplectic manifold and a Hamiltonian group action, we can consider symplectic reduction. So then, this unified Sokolov reduction is basically the symplectic reduction of, well, exactly the data I've explained. And it turns out that one goes kind of from omega g to orbits, and one goes from this boundary action, which is the only thing kind of surviving, it takes the form of the Schwarzian. Okay. So, but why am I telling you kind of this story? The story now gives us kind of an idea of what kind of operators we may look like, right? And how so? Well, so we can just basically ask ourselves, are there observables here, or parts of observables, or things which kind of descend to good observables in the Schwarzian theory? And in particular, there was a question? No? Okay. So in particular, observables in the F theories can be, like, very nice observables are Wilson lines, right? So our observable is something like path-ordered exponential of A. Let's say we take a Wilson line between the point x1 and x2. And since we localize over flat connections, which in particular are kind of written as G minus 1 dg, we kind of get that this is just the product of matrices. I think here's 1 G of x2. And so now, since these elements, right, they're just group valued, they take values in SL2R, we can look at the matrix actually computed. It turns out that there's a component which is invariant on a right ln action just by right multiplication of G. Okay? So this is ln invariant, where g goes to g times n with n and ln. So if we are doing the reduction by ln, this component doesn't change. So this is the good kind of observable in the sense that it descends to the Greenfeld-Sokolov reduction, right? So it descends to the Schwarzian theory. Okay, so it depends on 2 points. So it's actually this bilocal operator, which one finds in the literature. Okay. But now, if one goes through the calculations, we are interested in how does it look like in our free field coordinates, right? Because of course we found free field coordinates, but probably this is some horrible expression which we can just not calculate the correlation function of, right? So let's recall that we have these free field coordinates, so b is smaller than 0, c is bigger than 0. We have the f variable or field, which was just the exponential of the diffeomorphism. U was the logarithm of f prime. And then it turns out that in these coordinates, this bilocal operator, it looks like f of x2 minus f of x1 over f dash x1 f dash x2, and here's a square root. And in terms of the u variable, this is minus 1/2 u of x1 plus u of x2 integral ds between x1 and x2 exponential u of s. And kind of the picture we're thinking about, like pictorially, one can represent these nicely, kind of the situation in the BF story, so like on the disk, where we have the Wilson line connecting 2 points on the boundary. This doesn't look too bad, actually. So I just want to make a remark here. Yeah. So in particular, this is SL2R invariant, and if one looks at this expression in terms, for example, of the f variables, maybe one has seen it and one can believe it. But since we know it just, descends, it is just given because this is invariant. Okay, so now the task is, in the last 10 minutes, I think, to calculate and say something about correlation functions. So let's start with kind of the easiest, which is the partition function, which is now an integral over the u exponential, and let's scale the action s of u, where the action looks like minus 1/2 integral u prime squared dx, and t, okay, it's basically the central charge, but for the physics audience, like if you go through dimensional analysis, actually we need a dimension-full coupling constant here. So let me just write it c times something which has the dimension of length. Okay? But now I will forget about it and just say that t is basically equal to c. So t is more or less central charge. So then this is just a Gaussian integral, right? And it evaluates to, for example, by method of steepest descent, to the following object, square root of the determinant of t times the Laplacian, right? So u classical here, basically it's a linear function, right? But it still has to satisfy this property that it's c of x plus L alpha, so basically u classical is just x times alpha. Okay, so we can plug it in, and what we find is that this kind of needs to be zeta regularized. This gives some constant, but in particular we find the behavior on t, which is exponential here alpha squared GL over half. And now if you would like to compare it, for example, so this partition function was known in the literature, so for example, it was calculated by Stanford and Witten, using a Duestermatt-Heckman argument or localization. So to compare it with the formulas, if you're interested, we take just the usual circle, and t is just 1 over this g squared, the coupling constant they put, and then we find that this is the exponential minus something like alpha squared pi over g squared over g, some factor, which is precisely the result they found. So I just want to say that this was done by Stanford and Witten, and let's say they were using some kind of Duestermatt-Heckman localization. And I just want to point out again that, okay, they did a localization, the Duestermatt-Heckman localization actually usually is like a sum over the fixed points, right, of the S1 action. We just have one fixed point, thus we just have one factor, but here we can just classically compute it, and the boundary conditions are such that, I mean, we just get a unique solution. So everything kind of works out here. Okay. So now the more interesting things are, of course, the correlation functions of these bilocals. And let me start with just one. So what can we say about f1, x2? So now, okay, this is 1 over z, the integral over du of exponential t of our action, and then we just plug in the form of our bilocal, namely this form here, right? So let me highlight this form. So we get minus 1/2 u of x1 minus 1/2 u of x2. And then we get the integral ds du of s from x1 to x2. But so basically now we can just multiply the exponentials, put everything in the action, and define a somewhat extended action. So this is just 1 over z, integral over ds, integral over du, e minus s tilde, which now depends on u and s. And this s tilde now looks like integral u dash squared t over 2. And then we have a bunch of sources. I think like this, yeah. Right? So this is still Gaussian, but in the presence of sources. So we can actually calculate it directly, and again, it will be something like 1 over z, exponential of s tilde or minus s tilde evaluated at u classical. Let me call it u classical tilde, because now it's the classical solution to the equations of motion given by this action. Okay, and then you have again this determinant. But now, let me just say that the equations of motion, they kind of look like u prime prime minus t minus delta of u minus x minus s plus 1/2 delta x minus x1 plus 1/2 delta x minus x2. Right? So here we just have the contributions from the sources. So this is supposed to be 0. These are the equations of motion. And in particular, from here, we find that if we look at how u prime behaves, let's say, around the point x1, right? So we look at u prime of x1 plus epsilon minus u prime of x minus epsilon, then this jumps. Okay? So it jumps by 1/2 and this t. So we just are integrating this equation from x1 minus epsilon to x1 plus epsilon. So this jump basically means that we have like a non-smooth classical solution. So actually it turns out that u classical is a piecewise continuous function. And it's kind of, it leads to an interesting puzzle, which we might talk about later, but it's not a smooth solution. Okay, and then let me just say that now we kind of can compute everything, and let me just flash the result. So if one then does the computation, then the bilocal is just, now you need to say, where's the big one? Where's the good? It has an exponential part, x21 over t plus alpha squared TL over 2. I'm very sorry, but I kind of really want to write this actually not so bad formula. So it's given by arrow functions. That's kind of the upshot. And exponentials. And x21 is just the difference. But this is an exact result. No approximation, no nothing. So we can now read off, of course, for example, that it just depends on the difference, etc. We can read kind of, yeah, a lot of things. To give a small remark, because I think this is an interesting point, in literature, one usually finds the operators on -1, okay? So the bilocals in literature, they usually, in the f coordinates, they look like something like f of x2, f of x1, prime, square root, and then f of x2 minus f of x1, probably up to some power. But now, if we look at them in the u variables, they look like 1/2 u of x1 plus u of x2 over this integral from x1 to exponential u of s. So now if we plug this in under the correlator, we would kind of have to lift the exponential, right? And we're back in some kind of Liouville theory, right? So here we cannot just like combine the exponentials into an extended action. We have to do a little bit more. So this is actually much harder to track. But now for the last 3 minutes, probably the outlook. So we can not only calculate explicitly correlation functions of one insertion, but insertions of 2 of these bilocals. And this is what we've seen in this conference quite a lot, kind of a very important object because it kind of can probe for chaos in the theory if we choose kind of the ordering of the points along the circle correctly. Okay, so in particular, we would have a time-ordered product where when I represent each of these by a Wilson line, we would just have this. So we do the time ordering anti-clockwise. So x1 small, x2 small, x3 small, x4. We can get an explicit result, so we have it. But of course the question is, what about these out of time ordered things, where we have, for example, x1, x3, x2, and x4, right? So the time order is just, okay, this is time ordered, this time ordered, and they're all time ordered. The out of time ordered is basically swapping more or less the order of x2 and x3. So now actually to calculate this thing, we have now 2 parameters which we need to integrate, and we still have an extended action, but now it just depends on these 2 parameters, and they kind of go between x1, x2, and x3, x4. But now here they can be in the overlap, right? Because, I mean, for example, we could look at the situation where sigma and tau are just in here, in the overlap of these intervals. But, so there are actually 5 cases, sigma tau, where they are both in the overlap, or one of them is in the overlap and the other not, or they just don't care. So these kind of integrals, they behave similar. These kind of situations behave similar, and these kind of behave similar. But the upshot is that we can actually find explicit results And these are given by some exponential, so there's some kind of sum plus some error functions. Okay. And now, if I have one more minute, I just want to say, thank you very much, what now the next thing is we're doing at the moment, and which kind of will be very interesting, and yeah, kind of doing, like, show that this is actually very useful, these coordinates, is, of course, we want to probe for chaos, right? And so how to probe for chaos? So if I understood correctly, and it was very informative for me to actually attend this conference, is that we analytically continue our results. This is quite nice, right? Because we have exponential, we have error functions, we can analytically continue. So in physics, as I said, the x1, x2, and x3, and x4, they're some kind of Euclidean times. And so we'd say, okay, we go from xj to I, let's say, t j plus some epsilon j, where the epsilon are small and are like some kind of regulators, but they're subject to this ordering which we choose. And then what we're supposed to do is kind of to say, oh, we look at the out of time ordered correlator minus the time ordered correlator, and we look at certain limits. And the limit will be that the central charge, those t, goes to infinity, and these epsilon, they're just small. Okay? And then the claim is that this goes as 1 over the central charge, or this large parameter, so in our case it would be 1 over t, exponential some lambda, and then there will be some kind of difference here. Okay, so it will be something like x, the difference between x2 and x3, because this is the problematic case. And there are actually two cases, if I understood correctly. So lambda being real, then actually lambda should be bounded, and we have chaos. Or lambda is actually imaginary, then we have oscillations and no chaos. And I just want to mention that there's this very nice paper by Julien Franjal and Manuel Villemain, where they actually observe that, so yeah, let me just write the names. The observation is that hyperbolic orbits are non-chaotic. Elliptic orbits are. So what we're apparently supposed to find now, so what our task is now and what we're going to do in the next days is just continue our explicit result and probe for this exponential lambda and see if it's actually imaginary or not. And with this, I would like to end. Sorry for going over time. And thanks a lot.
Thank you.